Well, thank you very much. And I'm very pleased to welcome you all to the featured lecture and to this evening's series of Lubbock lectures. It is my pleasure to introduce Professor Arun Majumdar, who is the J. Precourt Provostial Chair at Stanford University, a faculty member of the Departments of Mechanical Engineering and Material Science and Engineering, and Senior Fellow and former Director of the Precourt Institute for Energy. In October 2009, Dr. Majumdar was confirmed by the United States Senate to become the founding director of the Advanced Research Projects Agency, Energy, commonly known as ARPA-E, where he served until June of 2012. Between March of 2011 and June of 2012, he was the acting Undersecretary of Energy under President Obama. He was a senior advisor to the Secretary of Energy, Dr. Stephen Chu, on a variety of matters related to management, personnel, budget, and policy. And in 2010, he served on Secretary Chu's science team that helps to stop the leak of the Deepwater Horizon oil spill. After leaving Washington, D.C., and before joining Stanford, Dr. Majumdar was Vice President for Energy at Google, where he assembled a team to create technologies and businesses at the intersection of data, computing, and the electricity grid. Most recently, Dr. Majumdar led the energy review team supporting the Biden-Harris presidential transition. He is a member of the U.S. National Academy of Sciences, U.S. National Academy of Engineering, and the American Academy of Arts and Sciences. His research in the past has involved the science and engineering of nanoscale materials and devices, especially in the areas of energy, conversion, transport, and storage, as well as biomolecular analysis. His current research focuses on redox reductions and systems that are fundamental to a sustainable energy future, multidimensional nanoscale imaging and microscopy, and the application of AI techniques to the development and delivery of energy and climate solutions. The title of his presentation is Energy, Climate, and Sustainability, the Defining Issue of the 21st Century. Arun, I will hand it over to you. You have 40 minutes for your presentation, followed by about 10 or 15 minutes for questions.
Ron, thank you so much for, first of all, inviting me to give this lecture, and also for the warm and generous introduction. I know this is late for many of you, for all of you out there in UK, and I appreciate your stamina and staying in there, your staying power to listen to this talk. As the title suggests, I propose that this is the defining issue of the 21st century, and I'll try to explain why. Before I go into the challenge and what solutions there may be and why it is the defining issue, I just want to give a little historical context of why are we here. The human civilization is roughly around 10,000 years, although humans have been around for a long time, but civilization and agricultural, agrarian society, etc., it's been roughly about 10,000 years or so. So it's useful to actually have a perspective of that longer term to see where we are. And I'm going to show you 4 or 5 charts to tell you what kind of a world we have been in the last about 200 years, 100 years mostly, and how different is that from the past. So the first chart is what I call the human tsunami. This is the population of the world, which grew kind of, very marginally over the last, the slope was quite marginal, the last 10,000 years or so. And you can see a few dips more recently on pandemics. They didn't have the vaccines that we have today. But what is remarkable is it's just incredible rise in human population really over the last 100 years or so. And this population is going to asymptote to about 11 billion people by 2100 and 10 billion people by 2050. So we still have about 2 billion people to be added in the next 30 years to about 10 billion people or so. This is the human tsunami. And the Earth has never seen anything like this in the past. The second tsunami I talk about is the human consumption tsunami, which is captured, not accurately, but captured somewhat in GDP per capita, which is the larger curve. And that has gone up exponentially. And that has given rise to what our quality of life is, which is improved very significantly. Now, the GDP is not exactly the right metric to quantify the quality of life. There are better metrics. In fact, the gentleman who proposed the use of GDP in 1933, this is right after the Great Depression, warned against using GDP as a metric to measure human, the quality of life. But yet we do that. And if you take the product of the human tsunami and the GDP per capita tsunami, you get the global GDP, which has gone up just amazingly high since even 1870. Now, this consumption tsunami has, of course, been fed and fueled by fuels, by energy. And so along with this is the energy consumption tsunami. And I plot over here only the last about 200 years or 220 years or so. And what I plot over here is the rise in energy, but also sort of the timeline of when I was born in the 1960s. My children were born in the 1990s. My parents were born in the 1920s and 30s, and my grandparents were born at the turn of the century. And in just 4 generations, we have seen just absolutely dramatic increase in energy consumption. I also plot out there the life of Sadi Carnot, because this is a mechanical engineer. You all know the value of Carnot and the Carnot efficiency in Carnot engines, et cetera. And the reason I do that is because 90% of the energy that is used today is via heat. And 80% of the primary energy is sourced from fossil sources. And of course, that has now led to the 4th tsunami, or you can call it 5th, is the CO2, the carbon dioxide tsunami, which is the rate of increase is something that the world has never seen in the past. This is the history of why we are at where we are today. And the question is, what are the consequences of that? And how do is this something we want to pursue in the 21st century? So let me just and tell you a little bit about what has this transformed. This is what life was like about 200 years ago, and it was mostly an agrarian society, and we used to live off the land, and we used to travel by animal power. And this is what we have today. We have electrically lit and air-conditioned homes. We sit on our TV and watch Usain Bolt run the 200 meters. We have healthcare like we've never had before. The life expectancy has doubled. We have information on our fingertips, and we can go to the grocery store with 100 horses in a small little car, or go across the world with 100,000 horses in a matter of a few hours that would have taken a month. This is the world today, and there's no going backwards in time. And this is what is known as the Industrial Revolution, which started in the United Kingdom. And this is a revolution which went from horsepower to what we know today, horsepower. So if you look at any modern economy that is sustained by this, the energy distribution and delivery system are the arteries and veins of any modern economy, whether it's the electricity grid, which I call the Tesla Edison architecture of the grid. The architecture has not changed. The devices have, but the architecture is roughly the same. And the other source infrastructure that we rely on is oil and gas. And oil and gas is something that we move across the oceans with tankers, as well as pipelines, et cetera. This is, if you take this away, the whole economy and the modern economy kind of comes to a standstill, as we have seen a few times once in a while. So here's the pop quiz. What are the consequences and how much time do we have? If you now look at the future, what do we see? I'm going to throw you some numbers, and it's a quiz. There's no grading for this, but we all know 1 degree Celsius is the global average temperature rise since the pre-industrial level. It's about 1.2, but let me just round it off to 1. And we are now seeing the extremes of climate change and climate-induced weather extremes that are happening. And, that is worrisome because it's going to affect everyone. 2 degrees is the Paris Agreement that the international community agreed that if 1 degree is bad, 2 degrees is going to be worse, and we don't want to really exceed 2 degrees Celsius. And so that was the Paris Agreement in 2015. And thankfully, the United States has rejoined the Paris Agreement, and hopefully we can contribute to that. I'm going to give you a few other numbers. The next number is 800. And this is not 800 degrees Celsius. We're not talking about Venus or anywhere close to that. This is if you are to keep the temperature rise below 2 degrees, this is the budget of CO2 that we have left. 800 gigatons or 800 billion tons of CO2 is the global budget that we have left. The next number is 40. And this is the rate of emissions per year globally. 40 billion tons of CO2 per year, 40 gigatons. Now, here's a reference point. What is a gigaton? It's hard to imagine what a gigaton is. Now, here's a reference point. If you add the weight of all 8 billion human beings on this earth, all 8 billion human beings on this earth, if you add the weight, that is less than a gigaton. It's 0.6 gigatons. And we are emitting 40 gigatons of CO2 per year. And if you take the ratio, we really have 20 years left. And after that, we have to be zero. So that is a hard proposition. And the question is, where do the emissions come from? The emissions come from all sectors. So electricity and heat production, agricultural, forestry is almost the same as electricity and heat. Industry is 21. That's mostly cement, steel, petrochemicals, and other heavy industries, 21%. Transportation, we think, is a big emitter. It is, but is actually less than industries, 14%. This is global greenhouse gas emissions. And so here's the world we have inherited, and here's how much time we have left. And this is the magnitude of the problem. So the reason it is the defining challenge of the 21st century is because the 20th century paradigm has to be completely changed. And because this affects not only the energy sector, but affects the construction, agriculture, transportation, all of it. In fact, if you sort of step back and take a look at this, one could argue that whatever 10 billion people consume will produce gigaton scale CO2 emissions using the 20th century paradigm. And that includes, of course, electricity, heating and cooling, transportation, food, textile. Textile is projected to be 10% of the emissions in the future, water, cement, steel, and information, which is the digital age. If energy efficiency is not brought into the picture, this could skyrocket as well. This is the world that we are in today and that we are inheriting. And this is going to then, the question is, how do we move the needle on this one? How do we turn the ship around? So here is the National Academy's report, and this is very similar to the IPCC report. Let me see, there's a chat. Someone is trying to chat with me. Okay, what are the primary emission sources to agriculture, forestry? I could answer it now, but I could wait till later. The quick answer is that we have food wastage. 30% or 40% of the food is wasted across the world for different reasons in different parts of the world. In developed economies, it's at the consumer. In developing economies, it's at the supply chain. Methane is a big source of emissions from livestock. And so meat and deforestation due to growth of meat is a big challenge, and I'll come back to that later on. And so there are multiple sources, but agriculture, forestry, land use is a big deal. This is so coming back to this is the red curve is what we need to follow to keep it below global average temperature rise below 2 degrees. And what you see is that there's a big chunk out here called mitigation, which is you got to reduce the emissions. But reducing emissions is not enough. What is now projected is that we need negative emissions on the order of tens of gigatons of CO2 per year, which is from the atmosphere, directly sucking out CO2 from the atmosphere. And the combination of the two is critical to get to net zero emissions within this century. Now, as you know, this is for the world. The United States, President Biden has already proposed that United States need to be net zero emissions by 2050, and China has proposed net zero emissions by 2060. Now, these are aspirations which are important, very important to have that. But to achieve that, there's no sugarcoating this. This is not going to be easy. And I'm going to explain to you what are the positive news and what are the big challenges where science, engineering, policy are required. Just to sort of add to put salt on the wound, you know, the assumption was that while we are emitting CO2 from various sources, as we saw, our big friend around the world are these forests, like the Amazon forest, as well as the tropical forests in Africa, which are big sinks of CO2, and called the lungs of the world, of the earth, are these big forests. Well, that's the assumption. What is turning out to be, and there's some wonderful work that is being done in both spot measurements as well as satellite measurements. The top curve is the spot measurements, or multiple spots. And what they're showing is that while the African forests are stable, that means they are, you know, there's a net carbon reduction, CO2 reduction in the atmosphere due to that, the Amazonian forests may not remain as a sink of CO2, but could become a source of CO2. That is the spot measurement. The bottom chart is satellite measurement. This is from NASA satellites. We have two satellites, OCO2 and OCO3, and they only cover less than 1% of the Earth's surface once a month. We're woefully inadequate. But what they have done is they measure it over time and integrate it over 3 years. And what they're finding is that the story is even worse from the satellite measurements, that the Amazonian forests and the tropical forests in Africa may not be even sinks of CO2, may already be sources of CO2 as big or bigger than China. And so this is very recent, papers 2019 and 2020. And so what I'm trying to say is that while we want to have negative emissions, this issue underscores the need for negative emissions, because there's no other way to actually take these emissions out if these forests become sources of CO2. It's a little scary. So the question is, okay, you know, what do we do? Well, I'm trying to simplify this. One is to do mitigation, which is hope for the best. And I'm going to talk about that. And the second one, and this is something I learned from the BP oil spill in the Gulf, that you cannot just hope for the best and prepare for the best. You got to hope for the best and prepare for the worst. And the preparation for the worst is adaptation and resilience. And because it seems likely, there's at least a risk of exceeding 2. And a lot of people think that 2 degrees Celsius is already baked in. We should be then preparing for 2.5, 3, 3.5. And that is the adaptation and resilience that at least I would like to elevate that issue as much as mitigation, because we need both on equal footing. So what is the good news? The good news is the following. We have had 3 major breakthroughs which has evolved over the last 30 years. It took 30 years to come here. One is unconventional gas, which North America is blessed with, and they have been able to develop the technology to, when I say North America, it's United States, Canada, and Mexico. And now we can do shale gas, unconventional shale gas extraction, which at one time was thought to be totally crazy. But now we could do that, and that is cost effective. And a lot of people tell me that, why are you including natural gas in this mix of clean energy things? Well, it has allowed the United States to get off coal and reduce its emissions in that respect. And if natural gas, at least it's a temporary solution. And we can't, given the magnitude of coal use, at least in the United States and perhaps in China and India as well, anything to get off coal at this point that is affordable is a good idea. So I include natural gas as one of the breakthroughs. The other breakthroughs is the renewable electricity from solar and wind. Now, even though these are small percentages in the grid today, the cost reduction has been so dramatic, is that these are now becoming, around the world, in many places already, is the cheapest way to produce electricity. And the big yellow circles are the solar curve, how the cost has come down. The blue is onshore wind, and offshore is also coming down now. And the dashed black line is the electricity cost from natural gas. And this is the United States, which is the cheapest natural gas you can get. And so what is happening is solar and wind are becoming cheaper than natural gas. Not to say that we won't need natural gas, but they're becoming cheaper and receiving the maximum amount of investments in terms of new electricity growth. This is, by the way, a tectonic shift in the electricity industry. The last one is another tectonic shift that is happening, which is the cost of electric battery packs have come down even faster. And today it's about $120, $130 a kilowatt hour is the capital cost of a battery pack in electric vehicles. And in the next couple of years, it is expected, and we can see the glide path of lithium-ion battery costs coming down to $100 a kilowatt hour. Now, why is that in red and horizontal line? Why is that important? Is because at $100 a kilowatt hour, electric vehicles become range competitive and cost competitive with gasoline cars without any subsidies. And this is a very important milestone, because one could ask the question beyond that. If you had all the charging infrastructure, et cetera, why would anyone buy gasoline cars? Now, I'm not saying gasoline cars are going to go away, because it takes at least 20 years for the fleet to be turned over. So take 2022, 23 and add another 20 years, and we are going to see a major shift in going from gasoline cars to electric vehicles. Now, these are all the good news stories. This is absolutely remarkable, once in a century transformations that are happening in multiple sectors. And the question is, oh, can we address climate change this way? And the answer is no. That's not good enough, because climate issues and CO2 emissions are from multiple sectors. So what else do we need? We need much more. We don't have grid scale storage for multi-day seasonal storage. That has to be 1/10 the cost of lithium-ion batteries, and we really don't have technologies for that. Small modular nuclear plants at half the construction cost, at least in the United States, of what it is today. And this is something that, first of all, we need to stop shutting down nuclear plants, because they are the largest source of carbon-free electricity in the United States. Refrigerants are a big deal, because refrigerants, the HFCs that came out of the Montreal Protocol, have a global warming potential 2,000 to 3,000 times that of CO2. And the leaks and the growth of the air conditioning industry, especially in developing economies, are projected to contribute to about anywhere from 10 to 40% of the global warming in the future. Buildings are a big, a consumer of electricity and heat. And, people have been proposing net zero buildings, and nothing has really scaled. And that is because you got to have net zero buildings at net zero cost, so that it becomes affordable and hopefully, more affordable than regular buildings. And so this is something that is a very important factor on the demand side of energy. As I said, industry is a big deal. Industrial heat for cement and steel manufacturing, petrochemicals, and a lot of people are proposing hydrogen. I'll come to that in a minute, clean hydrogen. And then, of course, decarbonizing food and agriculture. This is also, and I'll touch upon this a little bit later on. But in addition to that, we need some carbon management at the gigaton scale. And that is either harnessing the natural biological cycle through forestry, these are called natural climate solutions, or directly taking CO2 from the atmosphere or from point sources and storing it in the ground or converting it to something else. But if you want to convert CO2 to something else, you need hydrogen. You need another energy source, because it is at the lowest free energy level. So this is the rest of the picture that we need to develop. So following that, in the new administration, our new Secretary of Energy, Secretary Granholm, launched last week the first of a series of what she's calling, or what the president is calling, Earthshots. And this is similar to Moonshot for President Kennedy, Sunshot for solar for President Obama, and President Biden has Earthshots. And these are absolute breakthroughs toward net zero economy. And the first Earthshot is hydrogen. And that is because in addition to clean electricity, we need a way to store, and we need a fuel that is free of greenhouse gas emissions, because that hydrogen could do long haul shipping and transportation in different forms. Once it is stored in ammonia or some other way, long haul transportation, ammonia and fertilizer, which is a big source of CO2, steel and metals and cement industry, or just for industrial heat. And so hydrogen is some clean fuel like hydrogen is going to be very important. So let me tell you what the hydrogen picture is and some of the research opportunities, and I'll show you a little bit about what's going on in my lab too. So there is already a hydrogen economy. Let me just put it this way. There are 70 million tons of hydrogen that are produced around the world, 10 million tons in the United States. 95% of that hydrogen is produced from natural gas. And this is using a chemical process called steam methane reforming. And that hydrogen, given the feedstock prices in the United States, which is cheap natural gas, is roughly around $1 a kilogram. And the heating value is $7.50. I'm using US units, million BTU, but this is $7.50. Just keep that in mind. But this produces CO2 emissions. For every kilogram of hydrogen, we produce 10 kilograms of CO2. And this is called gray hydrogen. Now, if you capture the CO2, you turn gray hydrogen into what is called blue hydrogen. There are now very colorful labels given on it. But the cost goes up to around $1.50 to $1.70 per kilogram of hydrogen. And potentially we can bring it down to $1.25. But of course, you cannot bring it lower than gray hydrogen because there's an additional cost of gas separation. In addition to that, this cost does not include that if you want to do it at scale, you need an additional infrastructure of CO2 pipelines, which most countries don't have. The United States certainly does not have the vast network of CO2 pipelines. And so this is a big deal that if you are to go that route, this may be one of the options, but you need a new infrastructure. The second one, where everyone's a lot of excited about, is using electricity to split water in electrolyzers and produce hydrogen. This is a high school experiment that you can do to produce hydrogen. The problem is the cost. This is called green hydrogen. Of course, is the greenhouse gas-free hydrogen will only happen when the grid is greenhouse gas-free, and the grid is not today. So the grid has to be decarbonized before we get to green hydrogen, and that is certainly the priority. Today, it is about $3 to $5 a kilogram, 3 times or 4 times more than steam methane reforming. Potentially, we can get it down to less than $2, but that is hard. And that is because you need a lot of energy to split water, about 40 kilowatt hours per kilogram of hydrogen. That's the enthalpy of splitting water, 286 kilojoules per mole. But the good news about here is that you don't need any additional infrastructure. You have the grid to be able to do that. You do need to decarbonize the grid at the same time, but the delivery of energy is by electricity, and we already have that. There's a third way to produce hydrogen, which is really attractive actually, is to produce hydrogen from natural gas. And that is by a process called methane pyrolysis, where you produce solid carbon and not CO2. And solid carbon can be formed in amorphous form or carbon fibers. And this is a topic of research today. And this does not need any additional infrastructure because you already got the natural gas pipelines to bring the natural gas. And if you can produce solid carbon, you can put it in a trucks and haul it away. And that infrastructure also exists. And this is not only potentially $1 a kilogram, but potentially cheaper whereas you can sell the solid carbon in fibers at some value. So this is the picture of what the options are to produce hydrogen at $1 a kilogram, but it really depends at scale on the infrastructure, because infrastructure is very expensive to build, and there are lots of social challenges in accepting infrastructure to go to your land. And so this is something that has to be kept in mind when we're looking at various options. I'm not going to go into the details of this curve, but to say that pyrolysis in terms of cost is I think something that is worth pursuing. There's a lot of investments going on in that in R&D. In fact, my own lab is developing fluidized bed reactors to look at catalytic breakdown of methane to form hydrogen and high value carbon, in this case, carbon fibers or carbon nanotubes, which are higher value than amorphous carbon. But this is still in research stage, early stage. But if this is successful, there's a lot of interest from the industry to be able to produce hydrogen and put pyrolyzers. So this is really developing the technology and the science and engineering foundation to develop the pyrolyzer technology. The big problem is, of course, once you grow carbon on all this catalyst, how do you remove the carbon? Because you want to regenerate the catalyst. And so we have developed, I won't go into the details of this, we have developed what we're calling a non-stick layer that where we put on the catalyst. And once you put on the catalyst, you can remove the carbon very easily. And this is just showing some early data on 5 growth cycles, that even after 5 growth cycles, we can grow the carbon nanotubes. Whereas if you don't put the non-stick layer, you don't grow anything or grow very little. So this is a very exciting technology. And of course, we're trying to not only develop this, but also patent it and hopefully license it off to various industries. Long duration storage, a big challenge. And this is for multi-day storage, because if you are going to have a lot of electricity from wind and solar, you need long duration storage. And how much do we need? Well, if you are at the x-axis out here is the penetration of solar and wind in terms of percentage on the regional grid. So if you're at 50%, you would need about 10 hours of storage or so. And if you're at 30%, which is in California, you need about 5-6 hours of storage. But if you're 80%, you will need about 100 hours of storage. That's about 4 or 5 days of continuous storage, and you only use it about 4 or 5 or 10 times a year. And so that is what is required. And of course, if you only use it a few times, then the capital cost has to come down. And so if you're at 80% of penetration of renewables on the grid, you will need 100 hours of storage only 4 or 5 times a year, and the cost has to be less than $10 a kilowatt hour. So what are the different options? Here's where lithium-ion batteries today. And that can take care of a few hours of storage at 30% penetration, which is what we are using today. This is the lowest limit of lithium-ion batteries. So the bill of materials, and you can come down to around $50 or $60 a kilowatt hour. This is where pumped hydro and compressed air storage is, and this is totally white space. We really don't have any options. And this is where new kinds of thermal or electrochemical storage, potentially hydrogen storage, needs to be developed. And this is in process right now. This is in R&D stages. The other thing is CO2 management. And CO2 is, we are producing a lot of CO2. We're not going to get off fossil fuel right away. And we need to capture these, because any CO2 that you put in the atmosphere will last there for hundreds of years and will be in the CO2 circulation of the Earth. And so today, the cost is, it's expensive. Coal-fired power plants, it's about $60 to $70 a ton of CO2, and that's at 15% concentration at the exhaust. For natural gas fired, it's about 8%. The cost goes up. And for direct air capture is 0.04%, and the cost goes up even more. This is log scale, $500 to $600 a ton. And this cost has to come down dramatically to be able to make it affordable. And this horizontal line that you see is our tax credit in the United States called 45Q. and that's what someone will pay you. So the cost has to be lower than the tax credit for anyone to be interested. And right now the tax credit is right below that. And so either we raise the tax credit or we reduce the cost, and we reduce the cost so that they actually make it profitable and scalable. Let me just tell you a little bit about direct air capture and where the state is today. Direct air capture today, no matter which way you go, with this high temperature, low temperature process, we use around 2,500 kilowatt hours per ton, or about 9 gigajoules per ton of CO2. Most of the energy is for heat, not for electricity. At that level, at 9 gigajoules per ton of CO2, if you were to capture a gigaton of CO2 per year, remember, we have to capture 10 gigatons, but even if you were to capture a gigaton of CO2 per year, you will need 9 exajoules of energy. Why is that relevant? Is because in 2018, if you look at the production of carbon-free electricity, nuclear, wind, solar, hydro, put together is less than 6 exajoules. So we will exhaust the whole carbon-free energy in just doing 1 gigaton of CO2. Clearly, that's not the right way to approach it. And the question is, how much more reduction can we get in the energy consumption? Well, the thermodynamic limit is 125 kilowatt hours per ton, or half a gigajoule per ton of CO2. And that's the thermodynamic limit. This is very simple, entropy of mixing, and that's the work. And we do not want to be at the thermodynamic limit because there are no rates out there. So if you were to have some rates in this, maybe you want to be at about 500 kilowatt hours per ton of CO2. So we have to reduce the energy consumption in direct air capture by a factor of 4 from where it is today to be able to make it even somewhat viable for scaling. And without scaling, it really doesn't matter what we do. What we grow and eat is very important. And I just want to touch upon this. There are innovations out here too. For every 100 grams of beef that we eat, we produce 25 kilograms of CO2. So if you were to consume a kilogram of beef, it's equivalent to driving a car, a gasoline car, for about 100 miles. And so this is a big source of CO2 because of the methane that cows produce. And also, if you look at the deforestation that is created, the combination of that has been captured out here. Lamb is not much better. And if you really want to reduce the consumption, you can go to nuts and peas and vegetarian food. I'm not proposing everyone becomes a vegetarian. I'm trying to reduce my meat consumption, but this is, this food consumption is a big deal. And the way it is going, this can only become worse because the meat consumption around the world is growing up somewhat linearly, but in some countries more than linearly. And that's at the bottom out here, China and Brazil, the meat consumption is going up quite a lot. And that is what is consuming. And so when people become, have more money in their pocket, they like to get their proteins from meat. And that's why the protein consumption is going up. This is a big deal. And the question is, what do we do? We can change our behavior, of course, and try to go vegetarian, as I'm trying to do. It's hard. But you can also innovate in this using science and engineering. And this is something that just came out of Stanford and has really picked up steam, is trying to emulate the heme. The heme is what gives you the hemoglobin in blood, which gives you the taste of blood. And what Impossible has figured out is how to grow that in E. coli, in yeast. And now they can basically produce the heme molecule in yeast in vats, mix it up with soy protein and other vegetable protein, and make the vegetable protein taste like meat, because the taste of blood is what we find meat so attractive for. And this is growing exponentially in the United States. And my vegetarian wife, my wife is vegetarian, she has now started to eat all of this and said, whoa, this tastes pretty good. And so I think you'll see some conversion, but this is still at a small scale. This really needs to be at the scale of the world. That is not just the United States and Europe, but China and India and Brazil, where meat consumption is actually going up. This is mitigation. I'm just going to very briefly talk about adaptation and resilience. It is very, and so this is some work that is going on. You can take satellite imagery, you can use deep learning, and we have a program called Deep Solar, where we can spot and essentially get the GPS location and size of every solar panel in the United States. We published a paper in Joule, and many countries are now, and many regions are looking at this. Now we know where all the solar panels are in the United States and the size of them. We are doing the same thing, and now this is the growth of the solar panels over the years, and this is Los Angeles area. We can also now use Street View from Google, and as well as satellite imagery from Google Earth, and find the distribution and the transmission network, as well as the wind turbines, the substations, etc. And now what we're doing is building the energy atlas, because what we really want to do is to figure out where the big hotspots are in terms of climate-induced weather events, and where could be the big risk of infrastructure failure if you have a big event like we saw in Texas. This is very quickly looking at Energy Atlas workflow. We also collaborating with Google to create what is called a data commons, that all this data will be hosted on Google and made available to the world for free. And so that others could use this data to do other things that we may not have thought about. And so this is something that we are working closely with them. And data commons is an open source data source that people could use. So if anyone's interested in Oxford, we can connect them to the Google folks up here. We are also now putting it all together. This is some work on looking at fire danger. And some of you may remember last year, we had a terrible summer with fires, and California was essentially covered with smoke. And that with the pandemic would just come, some people went a little crazy with that. Anyway, what we are finding is that undergrounding distribution network is very important to prevent the grid failures due to fires or even causing fires. What we're also finding out is the undergrounding rate is proportional to the local family income, household income. So there's an equity issue that is also very important. And so we're trying to highlight these issues in our work using machine learning, et cetera. Just coming back to this, whatever 10 billion people consume will produce gigaton scale CO2 emissions. And we are trying, and these are all the sectors. So this is essentially the whole economy. And this is why I call it the defining challenge of the 21st century. The whole thing has to move. And, I'm reminded of a book that our local, famed CEO, Andy Grove, who was the former CEO of Intel, and he passed away recently. He used to teach in the business school out here, wrote, "Only the paranoid survive." And I think this is a time where only the paranoid in the business community, and frankly in other countries, have to think about that. And he defined a coin called strategic inflection point, that there's a point in the life of a business or an industry or a nation when its fundamentals are about to change. And the fundamentals are changing. There's no question about it. And there's no looking backwards in time to look at data to find solutions. So the change, he also says, the change can mean an opportunity to rise to new heights, but it may just as likely signal the beginning of the end. And the question is, can we pivot? And these are the various inflection points that have been created. And the question is, can we pivot? And how do we even approach this? Because as I said, there's no going backwards in time to look for data to extrapolate to say, oh, that's the solution, because the solution is what got us in this mess. So this is where we try to experiment with new ideas, look for new solutions, leverage new technology that have never been used in the energy and climate field, look for first adopters and new markets. This also means taking calculated risks to fail. We will be failing, fail quickly, learn from failures, not just our failures, but other people's failures. And so the communication and it's very important. It is, previous competitors could become partners, and this is in the business community, and previous partners could become competitors. It is very important to be flexible and agile. It is very important to not only do startups, but most importantly, scale-ups. And that requires people with execution and vision. And at the end of the day, it's all about people and capital. And this, if you put all this together, is what we call our innovation ecosystem. And this is the time to innovate. We've got to innovate our way out of this mess. And so talking about talent and people, I'm reminded, and this since I'm talking to some Oxford students, I'm reminded of a book by Tom Brokaw, who talked about the generation, in this case, the American generation, called the Greatest Generation, who fought in World War II and went through the Great Depression, fought in the war, came back and built the American economy. And I think this is the time and opportunity, maybe not for my generation, but for the next generation, next several generations, to be the greatest generation of the 21st century. And I love these titles, there is no planet B. And so this is what we need of the next generation of people. And so, and to address that issue of the demand and the need, the Stanford University has now launched, we are launching a new school on climate and sustainability. And this got announced last year, and we are trying to put all that together to see how that school has to happen. Now, this cannot be a 19th century design of a school or a 20th century. This needs to be a 21st century, and there's no playbook for this, because all the 7 schools that we have today, whether School of Law, School of Engineering, School of Humanities and Sciences, School of Earth, they were all started in the first 63 years, and for the last 73 years, we haven't started a school. But this topic is so important, and there's so much demand for this, not only from our students, but from our partners outside in the external world, that we decided that this is the time to launch a new school of climate and sustainability. But there's no playbook. We are trying to figure it out and trying to make this plane as we fly. And so this is ongoing right now. I just thought I'll put this up for you all. And let me just end with a very famous quote from Martin Luther King, who said these words for a different reason. But let me just say it's so appropriate for this. We are now faced with the fact that tomorrow is today. We are confronted with the fierce urgency of now. In this unfolding conundrum of life and history, there is such a thing as being too late. Thank you so much.
Well, thank you, Arun. That was very, very good. We have a number of questions. I'm going to start with the ones that had the most votes. This is from Maria Huff. And reading her question says, given the disaster of a 3-degree C world, should we also be giving a very high priority to lowering GDP and retargeting our value systems on the UN Sustainable Development Goals?
So the question, if I understand it right, was to give up on GDP?
No, to focus on lowering GDP.
Lowering GDP.
Yeah.
I would recommend a slightly different approach. I would recommend not to focus on GDP, but rather to focus on other metrics like the Human Development Index, which the United Nations actually uses today. It was developed by Amartya Sen and many others to look at other metrics of quality of human life, which includes education, access to healthcare, life expectancy, access to clean water, and the income level collectively. And that goes between 0 and 1, Human Development Index, and it's got a very strong correlation with electricity use and energy use. But it asymptotes that beyond a certain energy use, your HDI doesn't increase. And it's asymptotes. And the US is way on the asymptote. And so we can certainly reduce energy consumption and life will not be worse off. And so the question is, how do we get to lower energy consumption without sacrificing HDI? And I think that may be a way to approach this. But we are frankly in a bit of a Ponzi scheme in GDP, because the GDP growth and population growth are going up together. What happens if the population goes down? How do we keep our GDP growth? And China is going to have a massive demographic problem because of the one-child policy. How are they going to sustain the growth with a lower population, with a large retirement population? No one's figured this out yet. So there's some major economic theories that are going to be questioned in the 21st century.
Okay, we have another question. This one is from Amanda Smythe. She was actually one of our speakers this evening. And she asks, how do forests become carbon sources rather than sinks? Is it deforestation and agriculture causing the problem?
It is deforestation and agriculture. It is, so agriculture could be, it's actually both. Deforestation clearly has a negative impact on climate, right? So we know that. But agriculture, if you have what is called tilling of the earth, produces a lot of CO2 that goes up in the atmosphere. And so there's a big push towards no-till agriculture to develop seeds that do not require tilling. On the other hand, agriculture, we grow crops every year. And that could be a sink for CO2. And in ARPA-E, there was a program developed called ROOTS. And the ROOTS stand for rhizosphere something. There's a whole acronym for it. And the idea was, can we develop our staple crops with deeper roots? Why deeper roots? Is because the carbon degradation rate goes down exponentially with depth. So if you can have deeper roots, you can grow the food, but at the same time store the carbon in the soil. And that would be the right way to use agriculture to not only grow food, but also address climate change and negative emissions. And we haven't quite got, of course, we're nowhere close to that, but that's the direction we should be going.
Okay, I have a question here. This is, I'm gonna sort of drill into the middle of the list here. This is from Graham Pink, and he asks, the carbon footprint of electric cars powered from fossil fuel electricity is not good versus the carbon footprint of petrol cars over 10 years of life. How do you solve this holistic problem?
Great question. Yeah, if you don't decarbonize the grid and drive electric cars, you're going to produce more emissions, but probably not pollution in the city. I mean, that's the only advantage you get. You don't produce pollution, but you're producing more CO2 somewhere else. So I think this is all with a vision and the hope that your grid is going to get decarbonized first, because we have solutions like nuclear or solar and wind and other sources that could be decarbonized. Carbon capture and from natural gas power plants or coal-fired power plants, if that technology could be in. So decarbonizing the grid seems like the easiest of all the options, not that it's going to be easy. And if that happens, then it makes sense for electric vehicles to use electric vehicles, because then the source of energy will have lower emissions. But in many parts of the world, the grid is, there's a lot of CO2 emissions, and using EV only helps in the local pollution.
Okay. I'm going to ask you one more question, and then, but there are still some additional questions in the chat. I think what Vicky can probably send these to you maybe, and you might take a chance to look at them offline and ask them, but I'll give you this one last question once again from Amanda. Is it realistic to rely on technology that doesn't exist yet in order to achieve net zero? Or parenthetically, or maybe we don't have a choice. Are the necessary technologies developing fast enough?
That's a great question. So do you deploy today and be done with it, or do you wait for something else to come up? And frankly, I don't think we should fall in the trap of either or. We don't have the option to do, we don't have the time to do that. And so we got to use today's technology, whatever we have, but don't go completely whole hog into it and pin ourselves and lock ourselves out of new technologies. So I think it's very important today to build infrastructure, which is why we are hearing all this infrastructure bill in Congress in Washington, DC, infrastructure. And that's important. And that's because if you develop the next new breakthrough storage technology, you need the infrastructure of the transmission lines to be able to use it. And we may not have the solutions for the for the storage solution, but we can at least install the infrastructure so that once the solutions come, you can actually leverage them. And so I think it's very important to think through infrastructure, including pipelines, CO2 pipelines and all, and build that. So, and the idea is that if you're building a infrastructure today, like if you're building a highway, instead of building a one lane highway, you might as well build a 4-lane highway because of capacity that you would need later on. So I think that is very important. We have to use today's technology to get it moving, but we got to give it some room for new technologies to come through when they come through at scale, at speed, and so that they can be implemented as well. I mean, there's plenty of room of replacement or new things to come in. We're talking about the whole economy out here.
Okay. Well, thank you very much. I think the time is now, it's now 8:50 here. I guess it's lunchtime in Palo Alto. We thank you for joining us, and I'd like to thank all the speakers. I thought the presentations were extremely high quality this evening. I apologize again for the technical glitches. We are figuring this out as we go along. I like Aaron's comment about building the plane as you fly it. That's what we're doing this evening. So I want to thank Vicki and her team for at least keeping the plane from crashing early on. We managed to get through that. Thank Arun for joining us, and thank you all for joining us. And I wish you a happy evening. And for those of you who are leaving at the end of the term, I wish you also a very, very restful and productive summer. Thank you, everyone, and good night.
Thank you, Ron. Thank you all.